Everyone, John here, and for experiment 3, the goal was to analyze the second-order system using its transfer function and observe its response through MATLAB simulations. I defined the transfer function using the given numerator and denominator, then plotted the impulse and step response. So, from the results, I observed that the system response depends on the location of the poles. When the poles are in the farther left of the plane, the response becomes faster and settles more quickly. And when the poles are closer to the imaginary axis, the response becomes slower and more oscillatory. And also observe the pole location determines the stability. Poles in the left-hand plane are more stable, and the poles in the right-hand plane are unstable. So there are four system response I learned in this experiment, categorized as either overdamp, underdamp, undamp, or critically damped, which I'll discuss more here, and we'll use a second order system. I think only goes in a second order system. So the overdamp, you have your poles here, and your output is like this. I think this is much lower compared to the critically damp. And for the underdamp, you have your poles here, their partners with imaginary number, and your output is like this. It fluctuates and stabilizes. So for undamp, I think this is marginally stable because it's in the imaginary axis. And for critically damp, it's more faster compared to overdamp because it's 2.5 second compared to overdamp because it's negative 8.87 and negative 1.270 compared to negative 5 and negative 5. So one challenge I encountered was understanding how the transfer function affects the graph. At first, it was difficult to relate the coefficient to the response, but it became clearer after observing multiple simulations. So, as note to self, I learned that pole analysis are a reliable way to predict system behavior even without plotting. So, overall, this experiment helped me better understand system response and stability. And that's all. Thank you.